All right, I think we're ready to get started. Can the people in the Zoom meeting hear me? Great. Okay. All right, let's pick up where we left off yesterday. Or on Wednesday rather. So when we wrapped up on Wednesday, we were just starting to talk about this notion of happens before, and we introduced this notation, right, of A arrow B, which is pronounced A happens before B. And we said that what it means when we know that A happened before B is that A could have been the cause of B, right? But B could not have been the cause of A. And this is very important in being able to reason about how to debug and design distributed systems. But in the drawings that I did yesterday, when we were drawing machines and messages going between machines and so on, like this, the trouble with this kind of drawing is that you can't really tell which of those messages happened first just by looking at the drawing, right? So what we can do is actually make time explicit in the drawings that we do. And so we're going to introduce a new way of drawing diagrams today that allows us to talk about what happened before what. And so for that, so we're going to mostly not use this style of drawing, and we're instead going to introduce a new style of drawing, which we're going to call Lamport diagrams. Also known as space-time diagrams. So the idea of a Lamport diagram is that we have a notion of a process. And a process is just a line with a discrete beginning that goes on forever. And events are going to be dots on the line. So let's think of this line as representing a process, and let's think of these dots as representing events on the line, and time goes this way. So let's say I pick two dots on the line, say I pick two events on the line, say X and Z. Could X have caused Z? Sure, yeah, X could have caused Z. It happened before Z in that process. Could Z have caused X? No, Z couldn't have caused X. But do we know for sure that X caused Z? No, we don't. We don't know for sure that X caused Z. So, but we can use this tool of processes represented by lines and events in those processes represented by dots on the line to talk about what might have caused what, right? So given an event, all I have to do to find the set of events that might have caused it is look above it on the line. If I want to know why an event happened, something that's above it on the line was somehow responsible for that. But of course it's not that simple, right? Because we don't have just one machine. We have multiple machines. So let's make this a little bit more interesting, right? Instead of just one process line, let's have more than one. So let's say that we have, machine 0 and machine 1 and machine 2. So maybe on machine 1 we have our events X, Y, and Z. But then there's all kinds of other events that are occurring. So maybe on machine 2 there's an event P, and on machine 0 there's an event Q. And furthermore, because these machines don't share any memory and can't read each other's minds, they have to communicate by sending and receiving messages. In fact, that's the only way that these machines can communicate with one another, by sending and receiving messages. And message sends and receives are also events. In fact, they're very important kinds of events. So we can start to add some messages to this picture as well. So let's say that this event here, P, is actually a message send. So let's say that this is a send. And let's say that we have an event over here that's a message receive. And let's say we have another send and receive here. Maybe another one. So now we've got a whole bunch of events in this picture. Some of them are just what we call internal events, events that are internal to a particular process line. And then some of them are message send and receive events. So P, for example, is a message send, and T is a message send, and U here is a message send. And then S is a message receive, and Q is a message receive, and R is a message receive. And then events like, I guess, X and Y and Z and V here are internal events. So using this picture as a guide, let's try to come up with a general definition for when one event happens before another event. So we already covered part of it, right? We said that when we were dealing with just a single process line like this, then we said that if an event happens before another event on the same process line, or if it occurs higher than that event on that process line, then we know like that X happened before Z, for example. So that's going to be the first part of our definition. So let's write this out, and I'll move back and forth between this definition and this picture that I'm showing right now. So we want to say, given two events, A and B, we say A happened before B. Recall that this notation here of the arrow, A arrow B, is just pronounced A happened before B. We say that A happened before B if any of the following is true. First one is the one that we've already talked about. So A and B occur on the same process line. With B after A. So that's the first part of the definition, but there's more. Does anybody want to guess what other conditions, under what other conditions we can say A happened before B? Right. Right. So how could we write that down? Mm-hmm. Well, let's just handle the situation of sends and receives first. I think you're actually jumping ahead. So one way for us to say that one event happened before another, right, is let's look at, U and R here in this picture. U is a send and R is a receive, so U had to have happened before R, right? You can't receive a message before it was sent. Right, and we are writing the definition right now. So yeah, so we can say, for the next part of our definition, we can say A is a message send event, and B is the corresponding receive. All right, great. So we already know a lot of our happens before relationships. So we know that, X happened before S happened before Y, X happened before Y. We know that P happened before R. And we know that that message sends happened before their corresponding receives. So we know that P happened before S, and so on. But we're not done. There's one more part to this definition, which might have been kind of what this last question was anticipating. And so somebody in chat has actually already anticipated it. And so the last part is the part that makes this a transitive relation. So we say that if A happens before some other event C, and C happens before some other event B, because A and the B are the two that we're talking about, then A happens before B. So this last part here is what makes it a transitive relation. We call this the transitive closure of the relation. So to look at our picture here, so for example, let's look at two events. Let's say P and Y. So we know that P happens before S, right? Because P is the send and S is the receive. We know that S happens before Y because they're on the same line. And so we can put those two pieces together using that transitive closure idea and see that P happened before Y. And so this is a very powerful way of reasoning about what happened before what in a system. Now, importantly, it doesn't give us a way to relate all events in the system to each other, right? There are some events in here where we can't use those three rules that I just wrote down to necessarily give those events an order. But we'll talk more about that later. So this is the definition of the happens before relation. This is not actually an algorithm exactly for computing the happens before relation. Later on, we'll talk about ways to compute what is in the happens before relation for some set of events. So if we see some event, we'll be able to figure out what events happened before it, and we know that the cause of that event must be somewhere in that set of events that happened before it. But we'll talk more about actually how to actually compute the happens before relation later on. So here is a classic Lamport diagram. And it involves some strong language. So let's say we have Alice and Bob and Carol. And they're each a process. And let's say that Alice sends a message to both Bob and Carol. And let's say this message is, Bob smells. So Bob gets this message, right? And he can't really let this stand, right? So Bob has to say something in response. So Bob says, "Fuck you, Alice." Well, look what's happening for Carol here, right? Carol gets this "F you" message, and she hasn't seen this original message of Bob smells yet. So Carol is super confused right here. This is what's known as a causal anomaly. So generally speaking, anomalies are things that make you go, huh, like Carol is in this example. So we're going to talk about how we can use the concept of happens before to rule out such anomalies. So if you look at what went on here, you can see that this Bob smells message kind of took a while to get to Carol. Why? Why did it take so long to get to Carol? Sure. Yeah, so there could be any number of reasons, right? Which we talked about last time. So recall that we defined a distributed system as one that experiences unbounded latency. So if we're not careful in designing our systems, latency will lead to bugs. Actually, latency is going to lead to problems no matter what, since certain problems are literally impossible to avoid in a setting of unbounded latency. But this brings us to something else that I want to discuss, which is called network models. So it would really make life easy if we knew that there was some fixed amount of time that it took for a message to get from Alice to the intended recipient. It would sure make it easy to build a system that avoids this kind of bug if we had that kind of guarantee. Does anybody know what that kind of a system is called when we know that there's some fixed amount of time that it takes for a message to get where it gets? What that kind of a network is called? A synchronous network. So synchronous networks do exist. They aren't the kind that we're going to be spending most of our time talking about in this course, but they're worth mentioning at least briefly. So to be precise, a synchronous network is one where there exists an n, some number n, such that no message takes longer than n units of time to be delivered. So synchronous networks do exist. A synchronous network, for a message to be synchronous, there typically has to be some sort of stable circuit between the sender and the receiver. But we're not going to be talking much about synchronous networks in this course. So this is one network model. we're going to spend most of our time talking about another network model. The asynchronous network model. So what's an asynchronous network? An asynchronous network is just a network where there exists no such n. So some folks are asking some good questions in chat. One question is, could an asynchronous network work as a synchronous network for large values of n? So often when people build systems, they make simplifying assumptions, right? So you might indeed, when you're building a system, decide to assume that it does behave synchronously for some large n. And in fact, if you want to, on your own, you can look up partially synchronous networks. Nancy Lynch has a book called Distributed Algorithms. Where I think she has a definition of this. We're not necessarily going to talk so much about partially synchronous because I don't want to confuse things too much. But yes, in practice, people make simplifying assumptions all the time about the behavior of networks. But in general, you can't assume that there is a particular n that a message is definitely not going to take longer than that n to be delivered on the internet. So both of these, when I say network model, a model is a set of assumptions that you use to build a system. Those assumptions might be more or less realistic, but you can't build a system at all unless you figure out what your assumptions are. So, so you need to decide: are we going to assume that we have an asynchronous network, or are we going to assume that we have a synchronous network? And if I'm asking you to implement some sort of distributed protocol, I haven't really told you what a protocol is yet, but let's just say a protocol is a set of rules that computers use to communicate with each other. If I ask you to implement a protocol and you need to pick a network model to work with, if you really want to ensure that your protocol is robust, then you should pick the asynchronous network model to work with, the least forgiving protocol, because you really want to you want to pick the model that will have the fewest sort of assumptions. On the other hand, let's say that I want you to prove that something is impossible. That I want to prove that some behavior in a system is impossible. This is something that Nancy Lynch does a lot, for example. In that case, what network model should you go for? So in that case, you actually want to pick the friendliest, most forgiving protocol, because you want your impossibility result to be as strong as possible, right? So if your impossibility result shows that something's impossible, even in the most forgiving environment, then you know that it's going to be impossible in the others too. So if I show that something is impossible, even in the synchronous network model, then surely it's also going to be impossible in the asynchronous network model, which is less forgiving. So those are network models. In this course, we're going to spend most of our time assuming that our networks are asynchronous. Whether this is a realistic assumption in daily life is kind of another question. So a question in chat, what do I mean by friendly? The friendliest, most forgiving protocol is the protocol that kind of makes the most assumptions that make reasoning easier. So again, like if we were trying to prove that some behavior in in a distributed system was impossible. If we prove that or prove that something was impossible in a distributed system, if we prove that it's impossible, even if we know that messages take no longer than n units of time to be delivered, then we know it would also be impossible in this other setting where there is no bound on it. Okay, so I think we're going to pause and do a quiz question. So for those who are in chat, I will share the link to the quiz question. And we'll take a few minutes to do that. About 20 responses to the quiz so far. We'll wait a few minutes longer. So for those of you watching on Twitch, this is the part where I ask my students in my class to do a quiz, like a one-question quiz. But what I should actually do is show the quiz question on the stream as well. So I'll figure out how to do that next time. All right, we're at almost 100 responses to the quiz, so I think that's probably good enough. We'll leave it open for a little while longer, but I'll move on. Let's talk about something else. Let's talk about state and events. So we said that a dot on a Lamport diagram is an event, right? But we didn't talk about state at all, right? Like, what if this process has some state? Before, when we were talking about messages between machines, M1 and M2, we said that M1 was asking a question, right, about the value of x, and we were saying that M2 happened to know or believe that x was 5. So there isn't really anything in this picture over here that captures that, right? That captures this this x equals 5, this piece of state. So if you wanted to, you could kind of just like write it down right here. You could say, oh, this process happens to be M1 or M2 rather. Maybe M1 is over here. And then the way that this exchange of messages might look would be like this. And then if all goes well, M2 is going to respond with the answer. But what I would argue to you is that, well, let's talk about what state means, right? What is a state that a machine can be in? Like when you study computer architecture, for example, what do you say that a state is? I didn't say wrong answers only. All right. So what I was going to say is that the state that a machine is in is something like the contents of the memory and the registers and so on. So that's the state of one machine. But in this world where events occur on a timeline like this, how are we supposed to talk about state? So I'm going to argue that a dot on one of these diagrams is also a state, in the sense that whatever the contents of a computer's memory are at some point is going to be completely determined by all the events that have happened up until then. So if M2 knows that x is 5, that means that there had to be some sort of an event somewhere on this process line. Maybe it was an internal event that made x be 5. So a point is an event, but it also represents a state. And we can always work out what state that we're in by looking back at the events that have occurred. So one way to represent the state that we're in is by looking at this sequence of events. So we can always work out what state we're in. So in principle, if I knew that all the history of events that occurred on M2, I wouldn't even have to write this down, right? Because this fact of x is currently set to 5 would be represented either by an event, maybe this was the event that set x to 5, or maybe there was some event that set x to 1, and then there were 4 events that each incremented x by 1 that were all internal events. But whatever it was, there was some sequence of events that sort of boiled down to being a state. So a point is an event, but it's also a state, and we can always work out what state that we're in by looking back at events. Is it possible to do the reverse? If we know right now that x is 5, is it possible to work out what sequence of events led to that? With limited resources, probably not. So that's kind of all I want to say about state and events. When we do these diagrams, we are often actually going to write down little bits of state, like this, x equals 5, on the diagrams themselves. But just think of that as a sort of shorthand for some actual sequence of events. So this sort of diagram is actually very, very expressive. And if we wanted to, we could represent everything that ever happened just using this visual language of process lines and messages and events. So this piece of state that I'm writing down up here, this x equals 5, just think of it as a shorthand for something that I could have expressed using this very simple visual language. Okay. So I think probably everybody who was going to respond to the quiz has responded, so I'm going to close the quiz now. And let's just quickly recap the definition of happens before. So in chat, let's just define the three pieces of the happens before relation. So somebody blurted out. What are parts 1, 2, and 3 of this relation? Yeah, let's say, so A and B are actually events. So we don't say A receives a message from B. We talk about processes receiving messages from each other. But we're going to say A and B are events. But you're on the right track. So we say if A is a send and B is the corresponding receive. Then we know that A happened before B. Okay, what else? Good, yep, so. Okay, and then what's the last part? Last part is the part, yeah, go ahead. Right. Sure. So that is what allows us to kind of put together the other pieces, right? So if you have, say, M1 and M2 here, and you have some events that happen on those processes, and let's say you have like event X here, and events Y and Z here, and X happens to be a send, and Y is a receive, then we know that X happened before Y because that's this second part of the definition. We know that Y happened before Z because that's the first part of the definition. And then the third part of the definition, this transitive closure piece, allows us to sort of glue together those first two parts of the definition to conclude that X happens before Z. And then this keeps going, right? So we could have more events here. So if we have another event here, we know that Y happens before Q. And we know that X happens before Q. We knew that X happened before Q anyway because they're on the same line. but we also have this other path by which X happened before Q as well. So, so this is the definition of the happens before relation. So this I'm not being completely precise here actually. So I've written down 3 different ways that events can be in the happens before relation. So strictly speaking, it's actually it's a little bit more precise than that. We say that it's the smallest relation, such that this is true. So what do I mean by smallest relation? So this page is getting a little crowded, so let's switch to a new one. So a relation, a binary relation, like the one that I'm talking about, is actually just a set of ordered pairs. So if we're talking about some set of events, let's say, so putting some events here, let's just say that we have A, B, C, and D. Let's say that these are the events that we have. So let's just try to write down the happens before relation. And by that, I just mean the set of pairs of events that are related by this happens before relation. So what are they? Well, okay. Well, we know that A happens before B, right? Because A is the send and B is the receive. So we can put that pair. And then we know that B happens before C, right? Because B is before C on the same process line. And then we know that A happens before C because of transitivity. And we know that D happens before C, right? Because D is a send and C is a receive. Is that it, or did I miss any? So somebody asks in chat, should AD be in there? Did A happen before D? Do we know that? Yeah, so we don't know that. There's maybe it did, right? But we don't know for sure that it did. Maybe it kind of looks like it did, right? Because I kind of, if this is time in this direction, then it looks like D appears a little bit lower than A in this picture. So it might indeed look as though D happened before A. But our definition of happens before does not tell us anything about whether A happened before D. So this pair is actually not part of the happens before relation for this. So for this particular set of events. So this gets back to what I was saying about smallest relations. So we said that there were 3 conditions under under which a pair of events could it be included in the happens before relation. So the 3 possibilities, just to represent them visually, are either the events are on the same process line, or one of the events is a send and the other event is the corresponding receive, or it's the transitive closure of the of those things. So those are the possibilities. But we say that the happens before relation is the smallest relation. And so if you think of a relation as just being a set of pairs, I'm saying the set, the smallest set, such that all of these things are included in it. So if I didn't have that condition that it had to be the smallest relation, such that all these things are included in it, then I could say, oh, well, okay, I've got all these things covered, but then I'm also going to throw all kinds of other garbage in my happens before relation as well, and it'll still check all the checkboxes. It'll just also have other stuff in it as well. So we actually don't want to be that loose in defining what happens before means, um, because then stuff will be included in the happens before relation that we don't want. So that's why, if we're being pedantic about it, we have to say that the happens before relation is the smallest relation such that these three conditions are true. Okay, so let's do a few examples and think about what happens before what. So I'll bring back the picture that I had a little while ago. If I can find it. Here we go. All right, so let's look at this and let's just try to talk about what happened before what. So if I'm going to pick out two events, and you tell me if they're related by the happens before relation. So how about P and S? Are those related by happens before? Sure. Okay. Okay. What about X and Z? Yeah, those ones are as well. Okay. How about P and Z? Yeah, those are as well, by transitivity, right? Because we can get from P to S to Y to T to Z here. How about Q and R? Those are not related by the happens before relation. And so by that I mean, it's not true that Q happened before R, but it's also not true that R happened before Q. So we can write that this way. We can write the line with a slash through it. When this is the case for two events, we say that they're concurrent. And another way that's written is to put a double line between them. So sometimes people write it like this. And another word we use to describe it when they're concurrent is we say that they're independent. Questions about this? Okay. So we have about 15 minutes left. I want to talk a little bit about partial orders. So this relation that we've been talking about, this happens before relation, is a particular kind of relation. It's called a partial order. It's actually a special kind of partial order. but we'll get more into that later. Can somebody who's maybe taken a math class that studied this tell me what the definition of a partial order is? Some people are typing, so I'll be patient. You know, one thing about running class online is that it's possible to just paste a Wikipedia definition, isn't it? Yeah, so maybe we can come up with a definition that's slightly more intuitive. So partial order is actually two things glued together. So first, it's a set. Let's call it S. And then that set comes together with something. A binary relation. Usually, but not always, written like this, so something that looks like less than or equal. That lets you compare things. From the set S. And it has to have the following properties. Does anybody know this? What are the properties that that the binary relation in a partial order has to have? Can somebody tell me what one of them is? So actually somebody just said what the word that I was looking for in chat. So reflexivity. What does that mean? It means that for all A that are in this set S, A is less than or equal to A. What else? What else does a partial order have to be? Yeah, you can compare an item to itself, sure, and it's an item is less than or equal to itself. Okay, transitivity. Let's put that one last. So this says that, so I should put a for all up here. So for all A, B, and C in the set S, this is I'm not sure if you can read my writing or not, but this this symbol right here is this symbol right here is the symbol for in. So I'm saying that A, B, and C are in S, or are members of S. So transitivity says that if A is related to B and B is related to C, then A is related to C. That's what transitivity says. What am I missing? Yeah, something called anti-symmetry. Yeah, and what does anti-symmetry say? It says that if we're talking about A and B, so this is actually um, another way to put this. Um, is to say that if A is less than or equal to B and B is less than or equal to A, then A equals B. So if we're going to say that A and B are related in this way, and then also swapped around, if B and A are related by the relation, then A and B have to be the same thing. So those are the properties that have to be true of a partial order. I just claimed that the happens before relation is a partial order, but the happens before relation is actually a little bit weird, right? Because if we try to think about the happens before relation, which is a relation on events, and we try to think about how that fits together with this definition that I just wrote down, it's probably going to seem a little strange, right? Because a partial order is supposed to be reflexive, right? So a classic example of a partial order is just this plain old less than or equal to relationship on, let's say, natural numbers, right? So this is true of natural numbers, right? If we pick, say, the number 3, right? 3 is less than or equal to 3. That is true, right? 3 is also equal to 3, but that means that 3 is less than or equal to 3. But if we're talking about events in a distributed system, if we're talking about the happens before relation on events, it doesn't make any sense to say that an event A happens before A, right? And so the happens before relation is actually not reflexive. And so the happens before relation is a weird partial order that does not actually respect these rules. We say that the happens before relation is an irreflexive partial order. And so I actually feel kind of bad that the happens before relation is so fundamental to this class, to the point where it's the very first partial order that I talked about, because it's a weird one, right? It's not the partial order. It's not a partial order according to this definition. The partial orders are going to come up all the time in this course, and we're going to talk about some others as well. So don't get confused, right? The happens before relation is not quite a partial order according to this definition. Instead, we say that it's an irreflexive partial order. But if we look at these other properties, certainly transitivity is going to be true of the happens before relation, right? In fact, it's right in the definition that we wrote down. So we know that that checks out for happens before. And what about antisymmetry? Well, so if you have two events, right, and you say that A happens before B and also B happens before A, then A equals B. Well, yeah, that one kind of is that's another weird one in the case of happens before on a set of events in a distributed system, right? Because you're never going to be in this situation where A happens before B and also B happens before A. So this one, the antisymmetry part of the definition, like kind of also checks out in a sort of in a I forget the word that I'm looking for here, but it's true in a sense. So that checks out, but reflexivity doesn't. So so the happens before relation is not a real partial order. Have no fear that we will talk about some real partial orders later on. So there are lots and lots of relations that are partial orders. And whenever you talk about a relation being a partial order, it's useful to think about, okay, what set are we dealing with, right? If it's happens before, then the set we're dealing with is the set of events, right? And so in the case of this picture that we drew before, of a whole bunch of events happening in this system, then the set that we're talking about is Q, X, S, Y, T, Z, U, V, P, R, right? That's the set of events for this particular execution. And the relation relating these events, if it's going to be a partial order, then it has to have these properties. So as we said, for happens before, we took the easy one first, right? Transitivity. The happens before relation is transitive. It's right there in the definition. Antisymmetry, now I remember the word that I was trying to say before. It's kind of vacuously true, right? Vacuously is the word that I was looking for before. But for reflexivity, that's not true, because for that to be true, it would need to be the case that given an event A happens before A. So that's really not true, because it's not clear what it would mean for an event to happen before itself. So the happens before relation is actually not quite a partial order. It's what's known as an irreflexive partial order. And when you're talking about these irreflexive partial orders, you often don't use this less than or equal to notation to write down the binary relation in them, just to emphasize how irreflexive they are. Instead, you might just write less than instead of less than or equal. And of course, for happens before, we already have our own notation for it, which is this arrow. So these X's and check marks that I'm writing here, these just have to do with the happens before relation, because the happens before relation is the first partial order that we've looked at. I'm talking about how these three properties that are supposed to be true for partial orders, these two do hold up for that happens before relation, but this reflexivity one doesn't. And so happens before is not a true partial order. Instead, it's what we think of as an irreflexive partial order. So that's it for today. Next time, we're going to continue, and we're going to actually talk about another example of a partial order. And I'll see you on Monday.